Alright, so we're back, and this time I'm going to show you a few more examples. This is where we left off. We're talking about Lewis structures. Okay, so another example, let's go with carbonate. Yes, you can do Lewis structures for polyatomic ions just as well. Now, you can't do it for ionic compounds, but a polyatomic ion is a covalent compound with an ionic charge. So, carbon gives us 4 electrons. Oxygen gives us 6 electrons times 3 for a total of 18 electrons. And then its negative charge gives us 2 more electrons. Okay? So it's 18 plus 2 plus 4 is 24 electrons. Never forget the charge. Charge is super important. All right, so our central atom, our core atom, is carbon. Satellites are the 3 oxygen atoms. We draw 1 bond to each. That takes 6 electrons, leaving us with 18. Next, we're going to surround our satellites with non-bonding pairs. So 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay, so that's the remainder of our 18 electrons. We're out of electrons. So any remaining would go on carbon. There are none left, so no non-bonding pairs on carbon. But you look at the last step, you need to fill out the core atom's octet using double or triple bonds. Carbon right now has 2, 4, 6 electrons. Carbon is not yet happy. So what we do is we remove 1 pair of non-bonding electrons from one of the oxygens and make a double bond. Now, why did I choose that oxygen? No reason whatsoever. It literally could have been any of the other oxygens. But now, this oxygen only has 2 non-bonding pairs. That remaining non-bonding pair has been removed. So just to make that clear, let's go ahead and actually remove it. So, if you look at each of our guys, we now have a total of 8 electrons around each atom. So 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Okay? So all of the atoms in this molecule are happy. Are we done? Not quite. There's one last thing you have to do for a polyatomic ion. You put brackets around it and say, this has a 2- charge. So never forget the brackets around your polyatomic ions. Let's go ahead and do another molecule. Let us do dinitrogen monoxide, N2O. So nitrogen gives us 5 times 2 is 10. Oxygen gives us 6. So we have a total of 16 electrons. Okay. This one, you might be confused, but nitrogen actually goes in the middle. So you have a nitrogen on one side and an oxygen on the other. Okay. So that gives us, so that uses, I should say, 4 of our electrons, leaving us with 12. Okay. So now we start putting the remaining electrons on there as non-bonding pairs. 2, 4, 6, 8, 10, 12. That uses up the remainder of our electrons. So now we have a sort of difficult choice because this guy is still unhappy. Okay. We need to give him double or triple bonds in order to fill out the stable octet. The question is, where are we going to put those double and triple bonds? Because now it would matter where they come from. The nitrogen and the oxygen are not the same atoms, so you can't just choose one at random. So our structure could be nitrogen triple bonded to nitrogen, single bonded to oxygen. Or it could be nitrogen and oxygen, each giving double bonds. Or it could be nitrogen not giving up any of its lone pairs, but you have a double or triple bond on the oxygen. This is a little bit more difficult to figure out, but we will eventually discover the reason for it. It is this structure here. Let's go ahead and not cover up the non-bonding pairs. And why is it that structure? We'll get to that a little bit later when we start talking about formal charges. But for now, let's go with a different example. Let's do a perennial favorite, sulfur hexafluoride. Okay. Sulfur, if you look at the periodic table, is directly under oxygen. It has 6 valence electrons. Fluorine is a halogen, which means it gives us 7 valence electrons. And there are 6 of the fluorines, so 42 plus 8 plus 6 gives us a total of 48 electrons to play with here. Sulfur is in the middle here. So we surround it with our 6 fluorines. That uses up 12 of our electrons, leaving us with 36. Now, for the task that won't be even a little bit tedious, we're going to surround each fluorine with non-bonding pairs. That's 12. No, sorry, 6. Now that's 12. 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36. Okay, so that uses up our 36 electrons, and we're out. So we don't need to put any non-bonding pairs on sulfur. Now, do we have to fill out the stable octet with sulfur using double or triple bonds? No, because it already has 2, 4, 6, 8, 10, 12 electrons around it thanks to all those bonds with the sulfur atoms. So this is a happy molecule. The reason I call sulfur hexafluoride a perennial favorite is because when you inhale sulfur hexafluoride, don't worry, it's fairly safe to do so. When you inhale sulfur hexafluoride, it does sort of the opposite of helium. It makes your voice come out super deep because sulfur hexafluoride is incredibly dense. It's a very dense gas. You can actually, if you have an aquarium, filled with sulfur hexafluoride, you can float a paper boat on the sulfur hexafluoride. If you were to fill a balloon with the sulfur hexafluoride and toss it from one person to another, it would feel kind of like a water balloon. And yet, sulfur hexafluoride's a gas. It's interesting. You can find videos of this on the YouTubes if you care to do so. All right, let's go ahead and do another example. Let's go with, give me back my pen. Okay, iodine pentafluoride. Okay, so iodine gives us 7. Fluorine gives us 7. There are 5 of them for a total of 35 plus 7 is 42 electrons. Okay, iodine is right there in the middle. Let's go ahead and surround it with our fluorine. That uses up 10 of our electrons, leaving us with 32. Now we're going to surround our fluorines with satellites, or with non-bonding pairs, excuse me. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. Okay, so first off, that uses 30 of our electrons. So we have 2 electrons left, and those will go on iodine as a non-bonding pair. And that's it. We are done, because each fluorine now has 8 electrons and is happy, and our iodine has 12 electrons, an expanded octet, and it is likewise happy. Something to consider, just a practical measure. The way I've been drawing electrons, I've been drawing them as dots, so that they're slightly easier to see. So rather than just boom, plunking down a dot on your page or something like that, which might make it possible for your electrons to get lost, I recommend, whether you're using pen or pencil, go ahead and just draw a little circle. Doesn't have to be pretty, just enough that you can actually see it. And now let's go ahead, and it's a walrus drinking a milkshake. Okay, and let's do one last example. Let's do nitrate, NO3 1-. Okay? Nitrogen gives us 5, oxygen is 6 times 3 equals 18, and the charge gives us 1. Actually, I'm just going to keep on doing examples until time runs out. I think that would be the best thing to do. So 18 plus 5 plus 1 is 24 electrons. So nitrogen goes at the middle. We put the oxygens around it. And uses 6, leaving us with 18 electrons. So 2, 4, 6, 8, 10, 12, 14, 16, 18. So minus 18 equals 0. And we're out of electrons, but nitrogen is not yet happy, so we are going to have to go ahead and remove 2 electrons. Let's go ahead and do it from there. 2 electrons from one of our oxygens to make a double bond, and that makes our nitrogen happy. But we're not quite done. This is a polyatomic ion, so boom, 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 boom. And we have, not plus, minus. We have our finished Lewis structure for a polyatomic ion. And once again, we could have chosen any of these. These oxygens are all exactly the same, so the double bond could have been up top or down to the right, just as easily. Okay, now let's go ahead and look at the difference between ammonia and ammonium. Okay, so ammonia is NH3. Ammonium is NH4+. So, ammonia, nitrogen gives us 5, hydrogen gives us 1 times 3, for a total of 8 electrons. Ammonium, nitrogen gives us 5, hydrogen gives us 1 times 4, but this positive sign means we have negative 1 electrons. Okay, we've lost an electron. That's what gives it the positive sign. So 5 plus 4 minus 1 equals 8 electrons. All right. So ammonia, H, ammonium, H. All right, so the 3 bonds of ammonia cost us 6 electrons, leaving us with 2, and those remaining 2 electrons go on nitrogen as a non-bonding pair, because hydrogens don't get non-bonding pairs. Now, down here for ammonium, we have 4 bonds. So 4 bonds costs us 8 electrons. So we're all out. And the hydrogens don't need non-bonding pairs. The nitrogen is happy, but we're not quite done because this is a polyatomic ion. Okay, so that's the difference between ammonia and ammonium. I suspect that the reason that they sound so similar is because in other languages, they probably don't sound quite so similar. You know, in the German, it might be Ammonia versus Ammonium. Versus French, I don't know. It might be very, very different or very similar. Actually, no, in French, it's ammoniac versus ammoniac. That's even worse in French. But that's what they're called. And also, as you should have noticed in lab already, when you dissolve ammonia in water, you get this reaction. Oops. NH3 plus H2O forms an equilibrium with NH4 plus OH minus, or NH4OH. So really, these two, in most conditions, you'll find them are both present at the same time, which might be why there's some confusion regarding the name. All right, and we have hit the 15-minute mark. My timer's been beeping in my ears quite irritatingly for the last few minutes, so we will stop with our examples, and next time we will start talking about polarity.